So hi everyone, welcome to the Data Science Seminar. It's great pleasure to introduce Professor Muhammed Sayin from Bilkent University, and he's going to talk about learning in stochastic games.
Hello everyone, thank you for the introduction and thank you for the invitation. Today I will be talking about our contributions on the theory of learning in stochastic games. And let's start with some motivation. Right? Recently, we have seen a lot of progress in terms of AI technologies. We have seen some AI algorithms which can compete with top-level human players in complex board games such as chess and Go. We have started to see autonomous vehicles in real traffic instead of human drivers. And soon, with that progress, we will see AI in our daily life more often, right? But this can lead to some problems. Why? Because AI will now have this decision power. If you would like to use that decision power in our real life, this might have different consequences compared to using human capabilities in decision making. For example, this science article from 2021 shows that if businesses start to use Q-learning type of algorithm, which is a classical reinforcement learning algorithm, to make the decision about what kind of price to choose in their businesses, this can lead to some collision in terms of the pricing, meaning that AI algorithms, that Q-learning algorithms can learn to coordinate and increase the prices altogether, without any explicit communication between them. And this can be a serious issue, and we will start to see similar issues in different cases. In a nutshell, like we used to have some social systems with human decision makers. With the help of AI, we will start to see AI-powered decision makers, and now the social systems are transforming to socio-technical systems in which AI is also a decision maker. And AI has this is a different kind of decision maker. Why? Because they have more advanced computation capabilities, and this can lead to some issues. Furthermore, if you look at the settings from autonomous vehicles to complex board games or robotics, you will see that generally we will have a dynamic environment in which the AI agent will have a power to change the state of the underlying environment, right? Furthermore, we will have multiple AI agents interacting with each other in the same dynamic environment. This brings us to our main subject, which is the stochastic games. Right. I would like to introduce the stochastic games from a control theorist point of view, and we will start with a simple single controller. And our controller will be basically a function pi. That pi function, a control function, will take the state of the world, underlying environment, sk, as an input, and produce an output, which is the control input, ak. Right? Conditioned on the state, we will see a different control input. Furthermore, our controller will receive some reward. Usually we use the cost as a performance metric, but now let's call it a reward because we will be trying to maximize rather than minimizing it. And the reward will be depend both on the state and action of the controller. Furthermore, we will with the action of the controller, the underlying dynamic environment can have a new state, sk plus 1. And specifically, we will focus on the cases where the dynamic environment follows some transition kernel, in which the next state probability will depend only on the current state and current action, just like that. This is indeed a Markov decision process problem. If our controller also would like to maximize the discounted sum of the rewards collected over infinite horizon, the objective function will be written like that. And this kind of problems where we have a discount factor which takes a value in between 0 and 1 have many applications in control, energy, transportation, games, operations, finance, economics, and goes on. Because of that, we have seen many progress in that area. But in the reinforcement learning framework, we will have something different. The difference is the controller will not know the reward function. Controller will not know the transition kernel or transition probabilities. Because of that, reinforcement learning can address a wider range of applications in all those fields. Now, rather than playing with the uncertainty or model knowledge, I would like to go to another direction, which is a kind of orthogonal to that model knowledge. What if we have multiple controllers in the same environment? All of them will take some action, and their action will depend on the current state of the world, and they will receive some reward, but that reward will be specific to that controller, and that reward will also depend on every controller's control input. Furthermore, every controller's control input will determine the next state according to some transition probabilities. Right? By going in that direction, where we have multiple controllers in the same environment, multiple decision makers in the same environment, we can address a wider range of applications in those fields, from control, games, to economics. Right. Now, I would like to change the terminology. Rather than calling them controller, I will call them player, because I view them as an autonomous, intelligent decision maker. Furthermore, rather than calling it a control input, I will call it an action, and this will be the joint action or action profile. And each player's goal is to maximize the discounted sum of the rewards collected over infinite horizon, given that the other's strategy high. Right? I will denote all the players except player I as minus I. This is a shorthand notation used extensively in game theory. Right? This model is known as stochastic games, and originally introduced by Shapley back in 1953 in his seminal paper. Right? In that respect, stochastic games got very popular rather recently as well, especially because they can be an ideal model for multi-agent reinforcement learning. And going back to its introduction, since then, we also know that in stochastic games, specific to cases where we have finitely many states, finitely many actions, and a discount factor which takes a value in between 0 and 1, there will always exist a stationary equilibrium. What is a stationary equilibrium? Stationary equilibrium is the case where every player plays a strategy whose strategy depends only on the current state. The strategy does not need to depend on the time. This is stationary equilibrium. In that respect, this is very similar to the existence of a stationary solution for Markov decision processes, if you are familiar with that. And you can view stochastic games as a multi-agent generalization of Markov decision processes for non-cooperative environments, right? And this is a powerful result. But the key question I am interested in is, like, can we predict the outcome of intelligent decision makers' behavior in stochastic games by using stationary equilibrium? This is the key question I would like to answer. And to answer that, I want us to play hypothetically this game. Like, we will not actually play this game, but what if we have played, which number you would have chosen? Right? Suppose that I have asked everyone to pick a number between 0 and 100, an integer, and everyone will choose that number simultaneously. And we will collect those numbers. And then the ones closest to the 2/3 of the average will share the price. Right? I give you 5 seconds to think about which number you would choose in such a game. This game is a very popular game known as Key Beauty Contest, and it has been played maybe in every game theory classes to introduce the equilibrium concept to the students. And in general, interestingly, maybe because of the human nature, we observe that kind of histogram. Like, x-axis is the integers from 0 to 100. Y-axis is suppose that we have a large seminar room and we have many people attending. And y-axis will denote the number of people who selects that specific number. As you see, we see some peak around 33, some peak around 0. And the average, not depending much on what kind of population we are playing this game, generally the average will turn out to be around 27 and the winner will be around 18 or 17. Right? But what is equilibrium in this setting? The equilibrium is if everyone plays 0. Right? I also would like to briefly mention about the equilibrium. We will say that a game is at an equilibrium if players do not have any incentive to change their strategies. Right? If everyone plays 0, then they don't have any incentive to change their strategy. Why? Because the average of zeros is 0. 2/3 of the 0 is 0. By playing 0, you are the winner. By changing it, you will only lose the game. Because of that, everyone plays 0 is an equilibrium. But unfortunately, as you see, only a small percentage of people played 0, but they didn't win the game as well. Right? This can make us to question why we are interested in equilibrium. The reason is if those people played that game one more time or 2 more times, they will eventually choose smaller and smaller numbers and converge to the case where everyone plays 0. This is the common belief we have behind the equilibrium analysis. And back in 1990s, maybe even back to the introduction of game theories in the early 19th century, people generally ask this question, and this leads to the main question. Would non-equilibrium adaptation of learning agents reach an equilibrium in the repeated play of the game? Right? And today, I will rephrase this question and ask this. Would non-equilibrium adaptation of learning agents reach stationary equilibrium in stochastic games? Because stochastic games are very popular and ideal model for multi-agent reinforcement learning. And I am trying to understand, by using stationary equilibrium, can I have an idea about the outcome for the behavior of AI agents in a dynamic environment like stochastic games? And this brings us to our main topic, learning in stochastic games. Right? I would like to start this problem by making the connection between the repeated play of the games and stochastic games. Suppose that I define this magic value function. Like this V function will give us the value of a state. And that will be if the initial state is S, and starting from that, the opponents place according to some strategy pi minus I, and I will pick the best one, pi I. Then that will be the value of the state for me. Right? If we have a 0 discount factor, that value of the state would only correspond to the maximum value I can get from a game for which the payoff function is the reward function, and everyone else plays according to the pi minus I. Right? In that respect, like on the right figure, you see I've tried to provide some illustration. Suppose that we have 4 states, and this game will transition from state to state depending on the player's action. And occasionally we will the game will visit the same state again. If we have a 0 discount factor, that would mean that players would be playing a game specific to that state whenever that state gets visited. Right? But now we don't have a 0 discount factor. We have a non-zero discount factor. Because of that, we will use some dynamic programming type of approach and resort to the principle of optimality. And that will lead that the value of the state can be written as the immediate payoff plus the continuation payoff. Right? As you see on the right-hand side, we also have the V function. Therefore, this is a fixed point problem. If we can solve this fixed point problem, then we will find the value of the state. And I would like to give a special name to this term in parentheses to make it to make the notation simpler, and I will call it a Q function. Right? Since I have called that Q function, now I can write that fixed point equation in terms of the Q function. And as you see, the value of the state will be written like this. And as a notation, I will use the capital letter Q for the Q function. And the value of the state is basically the maximum value the player I can get in a game in which the payoff function is the Q function, and the others place according to that strategy. And the Q function is again will be the fixed point of this problem. Right? But now there's an issue. The challenge is, even though players will be playing some game repeatedly specific to that state whenever that state gets visited, the payoff structure or payoff function of that game will change in time. Why? Because the Q function is some endogenous parameter which depends on the player's strategies. Right? We cannot externally estimate that or learn that and use it as the payoff function. Whenever we change our actions or strategies, the Q function will also change. It depends on our strategies. And this makes it difficult to analyze. Right? To address this problem, we come up with this solution. The key idea is, what if we have some relative stationarity? Why? Because this endogenous parameter Q is not something observable. Like, we will not actually observe that. We will not actually receive it. We need to compute that. In order to compute it, maybe we will use some iterative algorithm to compute that, because that is basically a Markov decision process problem. In dynamic programming, iterative algorithms is a common approach to solve that kind of problems. And if we use that some iterative algorithm to compute that, what if we update that estimate related to the Q function only at certain instances? If there is some delay in the update of the Q function, whenever we have no update, for example, suppose we have an update at time 0 and we have another update at time 20 and no update between them, then whenever we visit that state, the players will have the same Q function estimate. From their point of view, they are playing the same game repeatedly. In that respect, maybe their learning dynamic will converge to some equilibrium. Right? And this is more like the repeated play of the same game, the same stage game between the Q updates. Now, I would like to smoothen this approach, this key idea, because it would be a challenge to coordinate everyone to stop updating Q function at certain instances and continue to update at certain instances. Like, this requires some coordination. How can we mitigate that coordination? That will be possible if you look at the solution at a closer level. This update rule figuratively can be viewed as there will be some jumps in the Q function estimates at certain instances, for like 0 and 20, and no jump in between that. But those jumps will be large. If I use some step size rather than making those kind of big jumps, but update it at every time instance, that will correspond to the update as if we are updating it only at certain instances, right? Furthermore, if I use some vanishing step size, which decays to 0, then this Q function updates will imply that Q function estimates are becoming relatively stationary from player's perspective, who plays the stage game. Right? That's the key idea. We will use some vanishing step size in the update of Q function estimates. In that respect, we can divide the game into two parts. In one part, players will be playing a stage game specific to that state visited, and they will learn about the opponent's strategy or the details of the game, stage game. And given that knowledge, now they will face a Markov decision process to compute the Q function estimates, and they will compute it at this part of the game and use that estimate in the next stage game related to the state visited. And since we have some decaying step size, Q function estimates will be relatively stationary. In that respect, maybe we can analyze the behavior of the players in the stage games as if Q function estimates are stationary. Furthermore, maybe we can analyze the Markov decision process, part of the game dynamics, as if the players, other players' strategies track the equilibrium. Right? This is the key idea. And why it makes sense? Because even when we have some relative stationary for the payoff function, I believe that the learning dynamics studied in the game theory literature will work well. Why? Because those learning dynamics are meant to explain how humans play. And since we are very rough player, that kind of learning dynamics must be robust against parametric errors, right? Like if we have a game, if the objective function gives us 5 or 5.005, it wouldn't make much difference for us. And that should also be the case for the learning dynamics. Because of this, I would expect our learning dynamics used for the stage games to track an equilibrium even when the payoff functions are only relatively stationary. And therefore, we come up with this idea: for stochastic games, players must use some 2-time scale learning framework in which they play the game, stage games at a fast time scale, and learn the Q function estimates at a slower time scale. And the key question is, we are trying to understand whether non-equilibrium adaptation of players reach some stationary equilibrium in stochastic games, but we come up with some solution. The question is that solution, whether that solution is consistent with our main objective, right? And if you look at the evolutionary game theory, there are some justification for that. For example, we have choices and preferences. Our choices are more dynamic. We can change our choices more dynamically. On the other hand, our preferences more stationary. We do not change them more as often as we change our choices. And choices can be viewed as our strategies in playing a game, and our preferences can be viewed as the value we give to the actions taken. In that respect, we can view preferences as the Q function. Therefore, it makes sense that maybe our choices evolve fast. Since they evolve fast, if we would like to learn them, we need to use a faster time scale so that we will be able to track the dynamic changes in that. On the other hand, since our preferences change slowly, we can use a slow time scale to learn them as good as possible. Therefore, we have this 2-time scale learning framework to address learning in stochastic games. And if you look at the related literature, the existing results are very limited, and I can classify them under 4th title. For example, the main cluster of work is about the computation of equilibrium in stochastic games, such as Littman's work for zero-sum games, or Wellman's work for general-sum games. They require some more very restrictive assumption in the computation of equilibrium in general-sum games. But apart from that, they are more computational tools. They do not look for addressing whether non-equilibrium adaptation of players would reach an equilibrium or not. Right? Furthermore, recently we have seen some work by Kostis Daskalakis to show that whether policy gradient type of approaches would reach an equilibrium in zero-sum stochastic games or not. But they use some asymmetric learning rules, meaning that one player evolves, updates his policies at a faster time scale, while the other player updates it at a slower time scale. There is some kind of coordination between them. Because of that, faster time scale will always have a strategy tuned to the slower time scale player, and this will help the slower time scale player to move the game toward, to move the dynamics toward the equilibrium. Right. On the other hand, I would like to focus on the symmetric learning rates in our 2-time scale learning framework. I am saying 2-time scale learning framework, but you must be careful about this. This is still a symmetric learning rate between the player. We have 2-time scale for within the player's own dynamic, right? There is no 2-time scale difference between the play of different players. There are also some other works, such as if Gürdal Arslan and Serdar Yüksel's work from 2017. If we restrict our focus to the stationary pure strategies, then a stochastic game simply can be viewed as a huge normal form game. And in that case, maybe we can consider that players are playing repeatedly that huge normal form game, and we can compute the solution. But unfortunately, stationary pure equilibrium do not always exist in every type of stochastic games. Also, there are some more related works, such as David Leslie's work and Bowden's work from 2022. They are about the best response dynamics in stochastic games, but they require some sort of coordination between the players. Because of that, they are not as reasonable, as justifiable as our work to address whether non-equilibrium adaptation of players would reach an equilibrium or not. I will be more explicit about this when I talk about fictitious play, and I am doing that next. Right. This will be our first main result, fictitious play for stochastic games. I would like to start with fictitious play. Fictitious play is a very popular learning dynamic in the learning in games literature, going back to the 1950s. And the idea is very simple. Suppose that the players assume the opponent plays according to some stationary strategy, right? This is some simplifying assumption. And given that knowledge, now I can compute that stationary strategy by looking at the history of the play. For example, I can just take the empiric average of the actions taken and say that given the frequency that action has been played, maybe the players has that kind of probability distribution to decide what kind of action they want to play. Right? This, I will call it a belief. Given that belief, they can take some best response to that belief. But rather than taking that kind of empirical average in which we count the frequency of the actions taken, we can also use some kind of iteration, like this and that are exactly the same. And I will view action as pure strategies in which we give a probability 1 to the action taken. Therefore, that action and the probability vector will have the same dimensions. This will be an iterative method to compute the belief or update our beliefs about the opponent's play. And given that belief, now we will be taking our best response in the game in which the payoff function is the reward function. Right, this is the fictitious play dynamics. Now, I would like to use that fictitious play dynamic for stochastic games, and the key idea like this. We have our dynamics have two parts. One is stage game part, the other one is the Markov decision. In the stage game part, players will follow the fictitious play dynamics like this, as if the reward function is the Q function estimate coming from the Markov MDP part of the dynamics. On the other hand, given the beliefs formed in the stage game part specific to that state visited, they will use that information pi minus I in the solution of the Markov decision process, and to solve it, they will use some kind of Q function iteration or value iteration by using this kind of update, in which they have a step size, and you can think this term in the parentheses as the first two terms in the parentheses will correspond to the Bandon operator in the dynamic programming, and they will update it by using that. Right? And the value will be the maximum payoff they can get if the opponent plays according to the strategy pi minus I. Right? In that respect, if we only have single state, then this MDP part is trivial, and the dynamics will reduce to the fictitious play. On the other hand, if we have only a single player, then the stage game part will become trivial, because the best response will always be the maximum one. There is no pi anymore. And the value iteration part in the MDP part of the dynamics will correspond to some Q-learning type of dynamic with some step size. Furthermore, I would like to emphasize that Here we assume that the players know the state transition probabilities and reward function, but they can also use a kind dynamic for which they don't need to know the model. And for example, rather than using this expectation term where we take the expectation with respect to the state transition probabilities, maybe we can sample the next state and use the state value for the next state in this update. If you do this, that will correspond to the Q learning dynamic. That will correspond to the Q learning update in the classical reinforcement learning literature, from the classical reinforcement learning literature. Okay, this is an informal statement of the theorem. Suppose that we have two-player zero-sum stochastic game and some standard assumptions for the step sizes, such as they will decay to 0, and they are not infinitely summable, but they are infinitely square summable. Also, we will have two-time scale learning, in which beta k, the step size we use in the update of Q function estimates, decays faster than the alpha k. If this is the case, furthermore, every state gets visited infinitely often, then we can show that beliefs formed will converge to some stationary equilibrium. Furthermore, the Q function estimates will converge to the Q function associated with that equilibrium. That is the case in two-player zero-sum stochastic games. In addition to that, we can also show the same result for multiplayer identical interest stochastic games with a single controller. We will have that additional condition for the identical interest case. Right? The proof is like this. This theorem is the combination of two results from two separate papers. And the first one is fictitious play for zero-sum stochastic games. Right? And I will try to give an intuition about the proof. In the original dynamics, we have two parts, stage aim part and MDP part. And we have two-time scale in which alpha, the step size used in this update of pi, goes to 0 slower compared to the beta, which is used in the update of Q function estimates. Because of that, if we use some stochastic approximation methods, we can show that this dynamics on the left-hand side can be approximated with the dynamics on the right-hand side, in which the time derivative of the Q function estimates are exactly 0. Right? Because beta goes to alpha faster than beta goes to 0 faster than alpha. Now, since the time derivative of the Q is 0, that will mean that we have a time invariant reward function in this dynamic. Therefore, this is exactly the best response dynamics in the continuous time. And there exist some results to analyze the convergence properties of that kind of dynamics in the literature. But unfortunately, convergence of this dynamic in the continuous time does not directly imply the convergence of this dynamic in the discrete time. To establish the connection, we need some stronger results, such as existence of a Lyapunov function. And Lyapunov function can be viewed like this valley. In this valley, the solution of like any trajectory of this best response dynamics will always go down within that valley. That will imply that eventually the trajectory will reach the minimum set of that Lyapunov function, right? And if that is the case, even when we have some perturbation, that trajectory will always be pulled down toward the minimum. And this discrete version can be viewed as a perturbed version of that continuous time dynamic. Because of that, it has been shown if we can find some Lyapunov function and show the convergence of the continuous time dynamic, that will also imply the convergence of the discrete time dynamic. But there exist some issues here, right? The issue is, even though we have a zero-sum stochastic game in which reward functions sum to 0, Q function estimates, since they are updated independently and autonomously, they do not need to sum to 0, right? Because if they were, then that kind of Lyapunov functions would solve the problem. But since they do not, we need to modify that Lyapunov function by penalizing how much the game deviates from the zero-sum structure. And if we do this, we can show that eventually the stage games will become asymptotically zero-sum. Furthermore, like that is the case, the Q function estimates eventually sum to zero in the limit. Furthermore, in the update of the Q function, MDP part, we can show that this operator will track that one, and that right-hand side is essentially a contraction mapping, just like the Bellman operator. And because of that, we can show convergence to the stationary equilibrium. And details can be found in the paper. Okay, what about the identical interest case, in which players have identical reward functions? We can follow the same steps, just like that. We need to use some Lyapunov function to again establish some tracking results, but there exist some challenges distinct to the identical interest setting. Firstly, in the zero-sum setting, it is very peculiar. Even when we have multiple equilibria, all the equilibria will have the same value for the players. This is something special to the zero-sum game structure. On the other hand, in the identical interest game, if we have multiple equilibria, they might have different values. Because of this, we don't know which equilibrium value they are going to track. That's a challenge. Furthermore, we will no longer have that contraction in the MDP part, which is very essential in the convergence analysis. We come up with a solution based on the observation that even though we don't have some contraction, even though we don't have uniqueness for the value of the game, we have some kind of monotonicity because of that Lyapunov function structure, like specific to the identical interest game. Particularly, the Lyapunov function for the identical interest best response dynamics will be something like this, which is essentially the value the players will get. Since we have that kind of Lyapunov function, that implies that the trajectory of the best response dynamics will always improve the value of the game players will get. Right? We have some kind of monotonicity in the continuous time. In this discrete time, we will not have that kind of monotonicity. It will be like a perturbed version of that monotonicity. And by using some algebra, we can show that that will not cause an issue. Furthermore, we need to assume that at least we will preserve the identical interest structure. If we do not do that, we will no longer have that Lyapunov function. We will need some penalty term as we have in the zero-sum setting. But we come up with this solution. We specifically focus on the games for which there is only a single controller. And a single controller stochastic game is this. Suppose there is only a single player who can control the state transitions, while the reward function will depend on every player's action. If that is the case, we can still show that this kind of dynamics will converge an equilibrium. Right. Also, I would like to emphasize another point. Going back to this one, right? I said that in the literature there exists some results by David Leslie in terms of best response dynamics for stochastic games, and I said that it requires some sort of coordination, and the sort of coordination will be like this. In the update of the Q function, as you see, we take a maximum. Here, in that dynamic, rather than taking the maximum, they will assume that the players will also form some kind of belief about their own play and use that belief in the update of Q function and assign the value by taking another expectation with respect to that belief rather than taking the maximum. If they do that, Q function estimates will remain will preserve the zero-sum structure, and they do not need to deal with the deviation from the zero-sum structure, and they do not face that kind of challenges. Also, that kind of dynamic in which a player forms a belief about his own play is not that natural compared to the case where they do not form a belief. Right? That's the key difference for our contribution compared to the existing literature. Okay, in the fictitious play type of dynamics, we assume that the players can observe the opponent's action. What if they do not observe the opponent's action? Can we still come up with some solution where the players only have some local information? For example, they only observe the state. And the answer is yes. And for this, we will use the individual Q learning rather than fictitious play. Therefore, I would like to first introduce the individual Q learning for repeated play of games. The simplifying assumption will remain there as in the fictitious play. And in the fictitious play, note that we have that expectation term. That expectation term can be written like as a function of the action taken. And rather than forming a belief about the pi, I can form a belief about that Q, little Q function. If I do that, I will have a payoff-based fictitious play. Right? I will just take the maximum for that little Q function and update the little Q function in a similar fashion, but rather than with respect to the action observed, I will use the payoff realized. Right? But there is a challenge here. The challenge is, since our update will only depend on the action taken locally, we will only be updating a single entry of the little Q function. And since we use some step size and different actions will be taken at different frequency, that will lead to some synchron issues in the update of little Q function. And this can be avoided if we use the individual Q learning introduced by Leslie and Collins back in 2006. And rather than taking the best response, they will take the smoothed best response, in which we have some regularization term, generally some entropy function. And that regularization term will ensure that there's a unique maximizer. Furthermore, that regularization term will pull the best response toward the uniform strategy where every action taken with the same probability. Right? And then if we do this, and if we also normalize the step by using the probability of the action taken in the denominator, then we can show that in the expectation, every entry of that little Q function will be updated at the same speed. And then it is easier to analyze its convergence properties. Therefore, we use that individual Q learning dynamics, since it is payoff-based, in the stochastic games by using the same structure. The only difference is, in addition to the reward realized, we will add that additional term where we multiply the value function estimates for the next state with the gamma, right? The change in the individual Q learning update will only be that part, highlighted part. And then we will update the value function in the MDP part by using the smoothed best response learned in the state game part. Furthermore, the little Q function estimate learned in that part. If we do this, we can show that this kind of update will again converge to the associated parameters of some stationary equilibrium of zero-sum stochastic game. Right? We will have similar assumptions, and all the convergence are almost true convergence. And finally, we have shown convergence to some equilibrium by using fictitious play type of dynamics in which players can observe the opponent's action. Then we have presented a dynamic in which players do not need to observe the opponent's action. What if, rather than converging to some equilibrium, what if I would like to converge to the best equilibrium for me with respect to some social welfare? And that will be the subject of efficient learning in stochastic games. And the idea is, if we use some log linear learning type of dynamics, we will be able to track or reach the efficient equilibrium, the optimal equilibrium, rather than some arbitrary equilibrium. For example, log linear learning can be viewed like a fictitious play with short memory, right? In the fictitious play, we used to form a belief about the opponent's strategy and call it pi, and given pi, we used to take the best response. Now, assume that our belief is the opponent will always play the last action, right? Given the last action, I will always react to that. And that is also known as cornered play. Now, in addition to that, I would like to introduce some friction to the problem so that actions will not change very often. If we do this friction, and we will do this friction by ensuring that only a single player will update his action while others will play the last action. Furthermore, the update of the action will be done with respect to the smoothed path response, where we have that additional entropy regularization. This dynamic known as log linear learning dynamic, and there's a good survey by Jason Marda and Jeff Sharma back in 2012, showing that log linear learning type of dynamics will reach the efficient equilibrium in certain sense. More explicitly, in the log linear learning dynamics, the joint action profile of the players will form some kind of Markov chain, and that Markov chain will be irreducible and aperiodic, furthermore homogeneous. And because of that, by ergodicity, we will know the probability that joint action profile takes will converge to some invariant distribution. And that invariant distribution or stationary distribution is very special. It will have that form, which is essentially the soft maximum of the reward function in the team problem, where everyone has the same reward, right? Our i's are all the same r, then the stationary distribution for that Markov chain will be this, right? That will imply that in the long run, at a higher percentage of time, which depends on tau, players will be playing the best action profile for the common team objective R. This is log linear learning. Now we would like to use that log linear learning for stochastic games. We will again do this in the 2-time scale learning framework. In the stage game, players will play log linear learning. Instead of using a reward function, they will use the Q function estimate. And in the MDP part, they will update the Q function by using the same update rule or a similar update rule. Rather than taking the maximum, they will use the action taken by the players. Right? If they do that, we will be able to show the convergence, but there will be a challenge. We will not be able to use that kind of idea. Why? Because the Q function estimates, different from the previous case, will be time dependent. They will be some endogenous parameter. Because of that, the Markov chain, like the action profiles, will not form a homogeneous Markov chain. We need to come up with some solution to this problem. As a solution, our idea is this: we will divide the horizon into T-length epoch, and then we focus on the accumulated iteration across those epochs. And we will define some filtration, which will include every information up to that time, right? 0, T, 2T, goes like that. If we do this and take write the update, T-step update like that, and then that innovation part of that update can be divided into 2 parts. One is the conditional expectation of that innovation part, conditioned on that sigma algebra plus some error term, and that error term will turn out to be a martingale difference sequence, which can be handled by using stochastic approximation theory. All we need to show is whether this part, this expectation term, track some efficient equilibrium or not. And the good thing is, since we look at the expectation term, what we are interested in the probability distribution of the joint action profile plate conditioned on that sigma algebra. Because of this, now we can establish some connection between the case where we keep updating the Q function estimates and the fictitious scenario where we do not update the Q function estimates in the beginning of the epoch, right? Like, I would like to repeat that part. To characterize the distribution of the action profiles within an epoch, I will compare the behavior of the dynamics in that original scenario with a fictitious scenario where players stop updating their Q function estimates. If they stop updating it, then the dynamics will reduce to the log linear learning dynamics, and we know how to analyze it. Now I will compare these two dynamics in terms of how much they differ. And the difference will be in terms of the Q function estimates. The fictitious one will always have the same Q function estimates, which is Q and T. On the other hand, in the original scenario, QT will keep changing. And the transition kernels will depend on the Q function estimates. Even though Q keeps getting updated, the change of that Q function estimates compared to the initial Q value in the beginning of the epoch will not be much because our step sizes are getting smaller and smaller. In time, they will be very, very small, such that our Q function estimates will be very similar to this Q function estimate used in the fictitious scenario. In that respect, the transition kernel in the original scenario will be very similar to the transition kernel in the fictional scenario. Because of that, we can show that the distribution of the action profiles will track the distribution in the fictional scenario, and which tracks the soft maximum associated with the Q function estimates. By using that, we can show that in the multiplayer stochastic team problems where every player have identical interest, under standard assumptions on the step sizes, if we assume that every state gets visited infinitely often, then we can show that Q function estimates almost surely converge to some epsilon neighborhood of the Q function, optimal Q function estimates. Optimal Q function. Why epsilon neighborhood? The reason is we are using the soft maximum rather than exact maximum in the which is inherent to the log linear learning dynamic, and this approximation error will be linear in the temperature parameter used in the soft maximum, right? Remember, this is the soft maximum. We have that entropy regularization. If we have tau small, that will be exactly like the best response, and this additional term will introduce some error, and that will be the case in our final result. Okay. The key takeaway is today I introduce a framework to combine big two literatures. One is learning in games with repeated play. The other one is dynamic programming or reinforcement learning. By combining these two framework, this literature, using our 2-time scale learning framework, we have shown that we can show convergence in 2-player zero-sum games, multiplayer identical interest games, model-free dynamics, payoff-based dynamics, and we can even have some equilibrium selection for efficient applications in engineering problems. And these are our recent contributions, and there are many future research directions within that area. If you are interested in learning more about this subject, I recommend you to check our website, and if you have any questions, you can always email me. Thank you.
Thank you very much, Sayin, Professor Sayin. Please, if people have questions, please type them in the question and answer box, or just raise your hand and I'll allow you to talk. So one thing that I'm kind of curious about, the zero-sum game or identical interest games might be a bit restricted for some economic systems. So do you have any ideas for more general cases?
That's a great question. We know that in the repeated play scheme, there are like fictitious play type of dynamics can also converge in potential games, or like we have other kind of dynamics as well. But generalization of that kind of results to stochastic games is a kind of challenge. The challenge is, if you remember our stage game part, go back. It'll be easier to realize, right? In the stage game part, even though reward functions have some structure, that will not imply that the Q function estimates will have exactly the same structure, right? In the team problem, if everyone have the same reward function, yeah, the Q function estimates will become the same, at least asymptotically. If everyone has a zero-sum structure for the reward functions, then yep, eventually they will become zero-sum as well. But for example, reward functions have some potential function. Since this additional continuation payoff part can be anything, and it will be depending on the value of the state, these two terms together do not need to have that potential game structure. That's the key challenge, right? And that it is an interesting problem to address, like how to define potential games for stochastic games. There exist some recent approaches to do this by looking at the stochastic games in the entire, as a whole, rather than state game wise, meaning that they will define a potential function for the entire game rather than a stage game. And it is also a kind of restrictive compared to its definition for the normal form settings, right? Yeah, that's a great question. Like, yeah, it is open for me. Like, we don't have existing results to address it beyond that.
Yeah, thank you. I see that Christian wants to talk. So, Christian, you have the permission to talk.
All right. Can you hear me?
Yes.
Yeah.
All right. Thank you. Thank you for the talk, Professor. I have two questions, if possible. One question that I have is, are there any results for like more general like learning behaviors? Like what if we look at strategies that are not stationary? Maybe agents like really care about the previous period, or they care about the previous K periods. Then I know that the sort of equilibria that arises in this case are much bigger. So yeah, that will be the first question.
Yeah. Within the learning context, I am not aware of it, at least for the stochastic games. Yeah, I believe, yeah, the thing is, it hasn't been studied much. Existing results are very limited. It started to get popular. Yeah, I think it is an open problem. Like, what would happen if you have different kind of dynamics, whether they would also converge or not. But this two-time scale learning framework can be helpful to address it.
All right, thank you. Yes, oh, thank you. The reason I asked that question is because going back to the article you cited from Science, where they are looking at collusion between different agents. Well, I believe that to address something like that, you will need like these kind of things I asked about. Thank you. The other question is, have you worked or are you planning to work or have you seen work, and what happens with when the set of strategies is not finite but infinite? Because most games are actually like the strategy space. It's a continuous maybe interval or something like that. So I haven't seen something like that so far.
Yeah, for that kind of cases, especially in the CS literature, there's a more recent trend to parameterize the policies, then learn those parameters, and the policies can be a continuum in that case. In that respect, like policy gradient-based solutions have become popular for stochastic games. Yeah, there are some recent results within that context. Yeah, if you are interested in, I can refer you. I don't know the exact paper names, but even Kostas Daskalakis' work in terms of policy gradient, I believe, was within that context.
I see. Thank you.
Yeah, thank you very much. Let's thank the speaker again, and we can follow up after the talk. Okay, yeah, thanks a lot.
Thank you.
Thank you.
Yeah, so Christian, do you want to follow up a little bit with Professor Sayin?
Yeah, I will have questions if he has time. That would be great.
Sure, yeah.
You want to do it now, or you want to do it at another time? What do you prefer?
Entirely up to the professor.